We're back, and in this lecture we're going to concentrate in on monatomic anions. Now anions, okay, are made from nonmetals, remember, and they're going to be negatively charged. And because of the way that we write formulas, the way we name anions looks a little different than the way we name anions. When we write out the formula for compounds that contain both cations and anions, the cation is always written first, the anion is written second. So to indicate that we have a compound instead of a mixture of elements, the name of the last element, the last ion listed, its name is altered from the pure element name, okay? To indicate that you have a compound instead of the mixture, then the name of the anion is going to look different than the name of the element, just by changing the ending. For anions made from a single atom, a monatomic anion, the last syllable in the name of the element is going to be changed to IDE. So the chlorine atom becomes the chloride ion. The INE becomes IDE. Okay? So let's look at our monatomic anions. Now let me scroll down. So oxygen, okay, which has a -2 charge, becomes the oxide ion. Sulfur, which has a -2 charge, becomes the sulfide ion. Nitrogen at 3- is called the nitride ion. Notice that the charge is not included in the name. You're supposed to know from the periodic table what column it's in, what charge it should have. So we have the fluoride ion, the chloride ion, the bromide ion, the iodide ion, the sulfide ion, the oxide ion, the nitride ion. Okay? All of their endings have been changed to IDE. So there they are written out for you. Hydride ion, fluoride ion, chloride ion, bromide ion, iodide ion, oxide ion, sulfide ion, nitride ion. Now let's talk about the size of ions. Monatomic cations are always smaller than the atoms they were made from. Monatomic anions are always larger than the atom that they were made from. So if you look at it, here's a lithium atom, a lithium ion. Notice it's less than half the size. And that's because you've emptied out the outermost shell and you shrunk it down so that the outermost shell on the ion is one shell smaller than the shell for the atom. Notice that the larger the charge, the smaller the ion. So the boron ion, the beryllium ion, and the lithium ion are all isoelectric with each other. The one that has the largest positive charge is the smallest. The one that has the smallest positive charge is the largest. If we look at the oxide ion and the fluoride ion, notice that the larger the negative charge, the larger the ion. It's not as dramatic as with the cations, but for the anions, the more negative the charge, the larger the ion. For an isoelectric series, a group of atoms, a noble gas atom and cations and anions that all have the same electron configuration, the more positive the charge, the smaller, the more negative charge, the larger. So if we were to look at the oxide ion, the fluoride ion, and then look at the sodium ion, the magnesium ion, notice that magnesium, those are all isoelectric. Magnesium is the smallest, followed by sodium, then it would be neon, and then fluoride ion, oxide ion. So in an isoelectric series, a series of atoms and ions that all have the same electron configuration. The more positive ion is always going to be the smallest. The more negative ion is always going to be the largest. Okay? Now, I want to talk about the terms paramagnetic and diamagnetic. A paramagnetic atom or ion is a particle with unpaired electrons, which allows them to interact with external magnetic fields. They'll be attracted to it. So like if you stuck a magnet to a bar of iron, that's paramagnetic. Diamagnetic is an atom or ion that has no unpaired electrons, which means they don't interact with external magnetic fields. Okay? So if we look at the periodic table, we need a periodic table. Let's see, do I have one down here? We go back up here to where we have a nice periodic table so we can look at it. Now this one will actually be pretty good for this. If we look at the periodic table, when we have pure elements, just no ions, the halogen family, the family that's headed by helium, called the halogen, the noble gas family, ends the very last column on the periodic table. Halogens, why do I keep saying that? Noble gases, or the inert gases, are all diamagnetic. They're not going to respond to an external magnetic field. As is the zinc family, which ends the D block, and the beryllium family, which ends the S block. So the last column in a block on the periodic table is going to be diamagnetic. All other elements on the periodic table are going to be paramagnetic. They're going to have at least one unpaired electron, which means that they're going to respond to an external magnetic field. The most paramagnetic elements are going to be those here in the middle of the transition metals because they're going to have the most unpaired electrons. Manganese has 5 unpaired electrons. If we count across here, 1 unpaired electron, 2, 3, 4, 5. Actually, chromium has 6 because of its weird electron configurations. But 5 unpaired electrons. That means we have a half-filled subshell. And then you add one more, 4 unpaired electrons, 3, 2, 1, no unpaired electrons. We look at the P block, 1, 2, 3 unpaired electrons, then 2, then 1, then no unpaired electrons. Okay? So, for these guys, if you have unpaired electrons, you're paramagnetic, no unpaired electrons, diamagnetic. If you're looking at an ion and you're not sure, write out its electron configurations, look at the end and see if you see a completed subshell or a partial subshell. If it's a completed subshell, it's diamagnetic. If it's an incomplete subshell, it's paramagnetic. Okay? Squeeze on by, make sure I've got everything in this chapter in. Yep. Okay guys, that ends the chapter. And we are ready to look at the next chapter. Take me a second to get there. We just finished up chapter 4. Chapter 3. We're ready to move into chapter 4. Okay? Here in chapter 4, we're going to start talking about chemical bonding. Once we understand the electron configurations for the elements, how many valence electrons they have, we can start taking that information about those kind of properties of each individual element, and we can use them to start talking about bonding. A chemical bond is a force that holds atoms together in compounds or alloys. So we care about electron configurations and trends on the periodic table because they're going to be our guide to understanding what atoms are going to combine with what atoms, and it helps us figure out the ratios that they'll combine with each other and the type of bonding that can occur. Now, the reason that bonding happens is that all atoms are looking for the most stable electron configuration possible and a minimization of the energy of the system. Really, I should say they're a minimization of the potential energy of the system. So let me add that in right here, potential. Okay, minimization of the potential energy of the system. Now, there are 3 types of bondings. It leads to 2 types of compound, and one bonding strategy leads to an alloy. So again, bonding is a strong attraction between atoms or between ions that leads to the formation of a compound or an alloy. We have 3 types of bonding: ionic bonding, covalent bonding, and metallic bonding. There are 3 categories if you think about it, because we have 2 main categories of elements, metals and nonmetals. So if you think about it, we can bond a metal with a metal, we can bond a nonmetal with a nonmetal, and we can bond a metal with a nonmetal. That leads to 3 different kinds of combinations. That means 3 types of bonding. Nonmetals combining with nonmetals is called covalent bonding. Okay? Covalent bonding leads to covalent compounds, and covalent compounds are made up of molecules. Metals combining with nonmetals is called ionic bonding, which leads to ionic compounds and the formation of arrays of ions. Ionic bonding does not form molecules. There are no molecules of ionic compounds. Okay? There are only ionic arrays. And we'll talk about that. Don't worry, I'll explain it better. When I combine a metal with a metal, okay, and I should have that up here. Did I? Yeah. When we combine a metal with a metal, metals combined with metals give us metallic bonding, which leads to the formation of alloys. Alloys look different than compounds. Remember earlier when we talked about compounds, compounds have a specific ratio of the constituent elements by mass. In an alloy, you can have a varying composition of the elements that are involved in the metallic bonding. So metallic bonding in alloys kind of sits on that fence between mixture and compound. Okay? So they're not just in physical contact with each other in an alloy, they're actually bonded together, but the ratio can vary even using the same 2 components. All right. Let's scroll down here. No matter what type of bonding is going on, the driving force behind it is the fact that the system wants to lower the potential energy. And after bonding, the potential energy should be lower than with the unbonded elements. So, our ionic bonding, okay? The ionic bond is the attraction between positive and negative ions. Ionic bonds then is the type of interaction we see going on between metal cations and non-metal anions. Because of the dramatic difference that metals and nonmetals have on their electrons, pure metals and pure nonmetals, when they meet, undergo